Welcome. I want to talk about the smallest distributed system, and probably in the literal sense as much as in the physical sense. It is really, really small. My name is Mathias Meyer. I go by Roid Rage on Twitter. There is no relation at all to steroids in this name. I work for a tiny company in Berlin called Travis CI. It is a hosted continuous integration system, and it started out as a very simple idea originally. That was by the end of 2010. There was GitHub was on the rise for sharing and collaborating on open source projects, but there was no platform around that gave projects the ability to run their tests, to have a well-integrated continuous integration platform that would, whenever a new commit came in or when someone contributed a patch, would take that patch, run it, and say everything is green with that thing. We started out as an open source project, basically a platform targeting open source products as much as our own code being open source. But we since then moved into the commercial space as well as supporting private projects. But that is not really what this is about today. I want to go back to 2011. 2011 was when we saw very initial traction. We had quite a few open source projects adopt Travis CI, and we ran about 700 builds per day. That included projects like Rails, a couple of smaller projects, but it was not a lot. All that ran off a single server. We had one box that basically ran all of the tests. It was virtualized using VirtualBox. It was a pretty ghetto setup in all, but it actually took us quite far. Yeah, and the application itself had a very simple architecture. It took a few weeks to build Travis CI. The ideas originally was to have, to add on to the status quo of continuous integration systems. One idea was that the user interface should be live updating, that when a build is running, you should see the logs stream and live. The UI should update as builds finished, as builds started, and something like that. Basically, it was supposed to have a nicer user interface than that other continuous integration system that was very popular and still is at that time. But it was supposed to make all of that freely available for anyone to use. Basically, when you had an open source project, you could plug it into Travis CI, and it would run your tests. And it would run them fairly well. So our original architecture was very simple. We had a web application that talked to the database. That web application was responsible for serving our API, for accepting new commit notifications from GitHub. Whenever a new commit is pushed to GitHub, we get a webhook notification from them saying, here's the new data that just came in, do something with it. That was what the web frontend was also responsible for. It basically took that payload and turned it into something that was runnable. And the component that was responsible for running that stuff is called Hub. It, in the end, turned out to do a lot more than that, but that's its basic function right now in this scenario. And there's a fourth component that's called jobs, which is basically an agent, a run agent, that was running on our one build server that would take new jobs, execute a couple of scripts in the virtual machine, and basically send a notification whenever it's finished. That component was also responsible for streaming build logs. So as a build ran, it would just sift off the output from the build and send it in chunks. And this is where Hub gets a little bit more complicated, because jobs basically only interacts with Hub, and the only thing it basically sends is that Hub sends jobs. Here's a new job, run it. What jobs does is it takes a job, runs it, streams the build logs and the build result, and that makes Hub already a little bit more complicated. We have a little orange rabbit down here, which is RabbitMQ, which is basically the single point of interaction between the jobs processing and the Hub itself. So it kind of became, much to my dismay, one of the central components in our system, RabbitMQ. And Hub would also, and that is a part where the live updates come in, Hub would also notify pusher. When new job results or logs came in through RabbitMQ, Hub would take these things and push them forward to pusher. Using pusher, we could then do live updates in the user interface. Then we push by now we push 50 million messages per day to pusher, but back then it was fairly minimal. But it was a great aha effect for people looking at the user interface to see all of that update in live. And Yeah, it's still a fairly simple architecture, but as you can see, it's already somewhat distributed, but it was built with good intentions in mind. It was basically assuming everything would work all the time and everything would work in ways that we can foresee and that we can expect. Unfortunately, that really didn't turn out that well. If we forward to 2012, we added one magnitude of builds. We're now at 7,000 builds per day. We've been adopted by a couple of open source projects, by a lot more popular one in the PHP world. We added a lot more languages. We added Erlang, we added Java, we added Perl, even PHP, Python. All the popular languages were basically supported out of the box. The problem was that with the platform being adopted more and more, we had a lot more responsibility to keep it running. Travis CI was originally built as basically an idea and as an ideal, and it was run by people as a side project, basically as something that people could use, something that, well, it would just run on its own, and we would just push a little bit of code every now and then. And unfortunately, that really didn't work out that well, because we started to have problems. We started to see problems in our architecture, and we started to see everything break at the seams, basically, in the very literal sense. And the biggest problem we had was actually visibility. The most embarrassing bits were, and that's when I joined Travis CI, was in the beginning of 2012, was that people from the community came to us saying, hey, my builds are not running. Or something isn't right. My builds are crapping out, my builds are erroring out, because we integrate with a lot of external resources. We integrate with dependency mirrors like Maven, Ruby gems, PHP's dependency system, Perl's dependencies, Python's, and so on. So we had people from the community approach us and say, this stuff isn't working. And that in the beginning turned out to be our biggest problem. We had no idea what Travis CI was doing. It was already a fairly big distributed system. We now had 10 build servers running tests, so we had a total of 60 VMs available. And that meant a lot of stuff could already start breaking at any point in time. And we had no idea what would break, and we had no idea when it would break, because we didn't have any visibility by means of metrics, we didn't have any aggregated logs, and we didn't have any alerting. And that was kind of embarrassing. It was embarrassing that people actually had to push us to look into things. And it was also embarrassing because we started working on a commercial version. Being notified by customers that my product is down is still one of my biggest nightmares. So we had to work a lot to actually make this happen. That was my first project, and it was the most important one, because in a distributed system, when you have no visibility, you cannot reason about what it is doing in production. That's why my biggest takeaway from this particular piece is that when you build the system, you need to think about monitoring up front. You need to think about how to monitor it, what to monitor for, and what to alert on. And that's not really what Travis CI was built based on. It was just assumed that it would just work, and that things would be running smoothly. And that things were running smoothly. And that was my biggest takeaway, that in a distributed system, even as small as it is, you need visibility. You need to be able to see what is happening in it at any point in time. You need to be able to reason about what it was doing at a particular point in time. And thankfully for us, this is a lot easier in a smaller distributed system than in a system that does the thousands of requests per second, that handles thousands of things in the background. In our system, which is still fairly small, it was easy to reason about what it is doing, but we actually had to work on making this happen. We had to work on adding logging, we had to work on adding the ability to trace requests as they came into the system, as they were handled by the system, to actually realize what is happening. Because it's become the central bit of our system, to be able to monitor it, to be able to run it in production. But the biggest problem we had was, once we had that monitoring, we actually saw things breaking. That's why visibility brings a little bit of a responsibility with it. If you see failure happen, you need to do something about it. Otherwise, you don't need to put in monitoring in the first place. That's why distributed system becomes somewhere of a notion that you accept that things break, and you accept that you have to do something about it. That was my realization of the last year. When things are broken, we have to do something about it. Unfortunately, things started breaking a lot. That was the downside. Our original little architecture in 2012 started falling apart. As we did 7,000 builds per day, we pushed a lot of log messages every day, and it just wasn't reliable. It kept falling over. It just kept, one component in particular kept falling over, and that's the hub. The hub was doing a lot of things. It was handling build logs, it was handling notifications. Basically, when a build is finished, we notify users that via email or via Campfire, via RSC, that of the build result. It was handling build requests as they came in from GitHub. It talked to GitHub. We interact with the API a lot. And it talked to Pusher, and it synchronized user data. One bit of Travis is basically to sync all of the data for a user that we have, all of the repositories that they have access to, and basically store that information on our end so that we know who has access to which repository. And Hub was a single process at the time. And a single process is not really a distributed system. And the problem with that single process was that it was impossible to scale out. We could not just fire up a new one and have all of this run in parallel. We had to have this single process. And it did a lot. It did actually fairly well. It did up to the log processing inside a single container, did up to 100 messages per second. But that really wasn't enough, because it kept us from growing. And one particular piece that has become very ingrained in how I think about distributed systems, I have a good example for, and that's the talking to the GitHub API. We're one of the GitHub API's heaviest consumers. We fire hundreds of thousands of requests to the API every day. And we assumed, when a build request comes in, we fetch the build configuration, which is stored in the repository from GitHub. We synchronize the user data with the GitHub API, and we update commits based on how a build went. In GitHub, you can have, when you have a pull request in GitHub, you can have a nice notification that the build has failed or it succeeded. And that's also what we do. We treated the GitHub API as a good friend. And this is more about the integration with the GitHub API than me bitching about that it is terrible. It is more, it is a learning point for us. We basically treated their API as a good friend. We called it and we expected it to pick up the phone and answer us pretty quickly and always answer, and pretty much always answer us. And that turned out to be a wrong assumption. It did not always answer us. It did not always answer us with the data that we expected. It did not always answer us with a reasonable result. It throws all kinds of crazy error codes in your interface. And at some point, about a year ago, things really started falling apart. That was one of our biggest outages a year ago. And that was because we used a somewhat undocumented feature of their API. That's where it already starts, but it was a feature that was added for us. And that feature at that time was simply disabled because it caused problems on the other end. On our end, it also caused problems because all hell broke loose and we basically stopped building anything. We stopped building anything because when a new build comes in, we go to the API, we check a few things that need to be ready for us to run the build. And that request, basically, we gave that request initially about, I think, 10 minutes. And on that particular day, the request actually started taking 10 minutes. All of our API requests basically started timing out, but the timeout was enormous. When we do 7,000 builds per day, we get, at peak times, we get about 1,000 build notifications per hour back at that time. So handling one build request in a setup that is basically just a single process and requiring 10 minutes to handle that single build request is not a great idea. It basically made everything fall apart. And the worst thing is, our build processing did not handle errors very well. So after the timeout actually hit, after 10 minutes, we would just drop the build request. We would just silently drop it on the floor and move on to the next one and time out again. It was not really great. It was a very long night for us to figure out what actually happened. We did have logs and we did have metrics at the time, but it wasn't enough to actually figure out this particular problem. What we learned from that was that all the external resources that we have, that we use, need to be treated as something that could break at any time. And that doesn't really mean that we need to protect ourselves from that. We need to put up a barrier and stop talking to the GitHub API. But that we need to have means in place to fail fast and to respond to these failures. Usually when the GitHub API is down or is unavailable, it's a temporary issue. It will come back within an hour. And for us, it started to be a business decision. Do we want to drop build requests when the GitHub API is down, or do we want to continue to function? And we decided that for our users and for our customers, it is important that these builds run. So we had to do something about that. What we basically did is we isolated all the API requests and we added shorter timeouts, much shorter timeouts. They're still way too long in one way, in their own way, but they're in an acceptable fashion. Basically, that particular timeout request is now down to, I think, 20 seconds, which is still a lot. But if it times out, we just ignore whatever that API call was supposed to be returning, and we continue doing what we wanted to do. But that itself was not enough, because it only allowed us to fail fast, but it did not allow us to, to retry, basically. The other thing that we added in response to that is after isolating it, when the request timed out with an error, we added retries to it. And to make it a little bit more resilient to problems in the GitHub API, and basically reducing the pressure that we put on their API, we added exponential backoffs. So this is a meme that has slowly emerged in our application, that not even talking to external components, but even talking to our own components. We treat them as something that we started treating them as something that can break at any time, that could plunge into chaos at any time. And there is an inherent uncertainty about using external APIs and even about using your own APIs. In a world where you move to basically service-oriented architecture, basically every application that you use is a means of uncertainty. They can break at any time. And because everything breaks at any time. It's the unfortunate reality of a distributed system, that things just break. And we started having to deal with that uncertainty, because Travis was built with very good intentions. It just assumed that networks would not partition, that APIs would always be available no matter how many requests we throw at them, and that our own components would always be available. And we had to learn from a lot of failures and outages that that's just not the case. So dealing with uncertainty has become one of my memes for distributed systems. Even when you have full control over the system itself, you cannot assume that everything is always running all the time, and that is always running well. There's always another problem. And at some point, they will come together and break everything spectacularly, like on this particular weekend. It took us a full weekend to figure out what happened with the GitHub API. And in the end, they basically flipped the feature back on their end, and everything was working again. That was an unfortunate weekend for us. But I want to get back to the hub and to our problem of just being able to run one process. Hub did all these things, and all on their own, they were pretty easy to break out. We could break out notifications, we could break out processing the builds as commit notifications came in from GitHub. We could push out synchronizing data with GitHub, because it's not really a concern that needs to be in the focus point of what is running, of what needs to run all the time. So we basically had all these blocks that we could basically just pull out of the hub, and make hub just a tiny, tiny, tiny box that by now really is only doing two things. It's scheduling builds. Basically, when new builds are available, it pushes them on a queue for the job process to run, and it processes the build results. So when a job is ready, the hub will get a notification, and it will do whatever is necessary to post-process that build. So now we had components that took care of synchronizing and talking to GitHub. When a build came in, components that handled the build logs itself, and components that handled all the build notifications, that sent out emails, campfire notifications, IRC, and all that. And that was pretty good, and it was actually fairly easy for us to do, because the responsibilities were already very isolated. So in the end, we ended up with very simple processes. We had very simple apps that we could scale out independently. We could add notifications process at any time when the queues were backing up. And the queues are always backing up. The other meme of the distributed system, there's always a queue that's way too full. So that was actually, we solved that problem fairly easily. It only took us a few weeks to break out these apps, which was very good. It brought an unfortunate problem with it, though. Our code is structured in a way that all of the business logic is in a single library. It's called Travis Core. And it's that giant box in the middle. And we have all these components around. We have Travis tasks. We have the tasks, which basically involves notifications, sending email, all that stuff. We have the logs processing. We have the API, which basically our web user or web interface talks to. We have Hub, and we have Gatekeeper, which takes care of synchronizing data with GitHub and handling when a build request comes in. And so we suddenly had this big ball of mud in the middle that all of our apps were depending on. So scaling out these applications suddenly turned into a dependency problem. Because this core library contained all of our code, all of the apps depended on it. And to make sure that every app was still working after we made a change to the code, we had to make sure that we deploy all of them. So there started to be a certain fear of shipping a new feature because of this giant big ball of mud in the middle. We paid dearly for a lot of architectural decisions. And what we wanted to do instead is focus on very small dependencies and very small responsibilities. We have the responsibilities in our applications already, they're just not in the code. The code is nicely separated and all, but it's still one giant library that all of these applications use. So it started to get into the way of us shipping things, us deploying things. It just became a matter of confidence. And that's why what we're currently working on is getting this big ball of mud, tearing it apart, and pushing all the responsibilities and the dependencies for that into the small apps. Because they're already fairly isolated. It's just the code doesn't reflect that very well. And that was an interesting revelation, that modularity is not just something that you have, when you separate apps, when you split out applications that are like little services that handle specific responsibilities. Modularity is something that is reflected in code, but it's also something that is reflected in your dependencies. If you have one big ball of mud like we do, you will have less confidence to ship code, because there's always a fear of that one change and that particular code could affect something in this other piece of code. And static analysis, all that kind of stuff, unfortunately wouldn't even help with that. So we're working hard on breaking all of these dependencies out fully, but it's a lot of work, unfortunately. And yeah, one of these components is worth a deeper look, because it turned out to be the biggest culprit of us being able to scale out. Because breaking all of this stuff out for Travis AI was not really just about having a distributed system. It was about being able to grow. We started approaching another magnitude of builds per day, and we could see back at the time that the architecture that we had wouldn't really cut it. Logs, in particular, is the more interesting example, because logs is the component that handled log chunks as they come in from jobs. It is traditionally it was one processor, and that single process was basically responsible for updating the database and sending the log chunks to pusher. And in our old architecture, updating the database meant updating a single row and a column, which contained the entire log. So whenever a new chunk a new part of the log came in, we would basically issue an update statement to the database and basically concatenate two strings together. It was rather efficient, but it meant one thing. It meant that this particular part of the code was depending on the order that the messages came in. It was always rely on that the messages came in into the right order. When they were out of order, suddenly you would have a broken build log in the database, and that was not very pleasant. And the same is true for our web user interface. Pusher, again, this is the other responsibility for the logs library. It sends the messages to pusher, which then in turn forwards them to all of the people that have basically a browser open and want to look at the build log as it tails in live. And how that usually works is we had this one logs processor, and we had all of these single build jobs that were basically pushing messages onto a RabbitMQ queue. The logs processor would take them one at a time and would update the database with it and would forward it to pusher. And this process actually did fairly well. At peak times, it would process 100 messages per second. It was already scaled out a little bit, so it used threads to be able to do things concurrently, but it was not doing very well. And 100 messages per second started being our daily average of messages that we did. So we could see that there's going to be a ceiling that we're going to hit at some point. And even when we have a queue backing up, because there's always a queue backing up, when the queue suddenly would get full and we would have a burst in log messages, that processor would not be able to catch up with that burst. So that started really turning into a problem. And the core problem of this entire process was that all of the log chunks were required to be in the exact order. You know, the logs processors relied on the log chunks to be in the exact order that they would appear basically in the build output. And relying on the correct order in this case turned into a scalability issue for us. If you need to rely on ordering, in a distributed system, you come into the realms of coordinating several nodes to find the right ordering of an event. But it turns out that we could actually do something fairly easy about it. And unfortunately, doing that had a lot of consequences for the rest of our system. But what we ended up doing is we made the ordering a property of the message itself. So rather than relying on RabbitMQ, on the message to be pulled off the RabbitMQ queue in the right order, we basically determined the order in the message itself. Every message got a clock, basically a counter, that would identify its position in the complete build log. And that made it fairly easy to assemble logs later. We had these chunks suddenly. We started storing, instead of updating a single column in the database, we would store the small chunks. And at any point in time, we could basically take these chunks and reassemble them again into a complete log just based on that counter. And it was quite a beautifully simple thing, because a job run is always just responsible for a single job. So we could make sure that we wouldn't have any conflicts between multiple job runners updating the same counter, which is another horrible problem I would like not to have. So we could keep this counter or a clock around, and it suddenly made things really, really easy. Writes were actually faster because we only wrote single writes, which in Postgres, which is our main database, means you just append something to the transaction log and you're done with it. It's basically an append-only write. And that was fairly beautiful. And I gotta say, the ideas from this, and this is where the Renaissance fits in. I got the ideas from this for this. It sounded like a fairly obvious idea, but the ideas for this are, the inspiration for that came from a paper from Leslie Lamport, which was called, what was it called? Time Clocks and the Ordering of Events. And Lamport in that paper talks about using a clock, which in this case can just be a counter. Even a counter can be a clock in this case. And whenever a message is passed from a sender to a receiver, the sender would increment a clock. So you could, when the receiver forwarded the message again to another process, it would again increment that clock. There are some certain intricacies involved in that, but the basic idea is just that. As a message passes through a system, that counter would just be incremented. It's the very simplest idea, and we could actually use this simple interpretation of what Lamport wrote about in our setup. We just needed this one clock to be able to identify a message later on, so we didn't have to worry about just leaving one logs processor running. We now have 5. We can process up to, I think our peaks are 300 messages per second, and we don't have to worry about reassembling the logs, because that simple counter is basically what allows us to do that at any point in time. It had big effects on what our web user interface was doing, but it was worth the trouble. And that's another thing for distributed systems, one of my main learnings, simplicity. If you can make things as simple as possible, they will be easier to scale, and they will actually be easier to reason about. Having to reason about the ordering of messages having to process them without having an explicit order is for me a matter of complexity. And I think Rich Hickey would actually agree in this case. He dislikes ordering, having to rely on order. He calls it one of the things that complect, and he does use complect software systems. And so this little means, just putting a counter into the message, allowed us to actually scale out this beautifully. It forced us to update the user interface, because the user interface was also just taking these events and appending them to the DOM, as builds were trailing it live. But it worked fairly well. We had two approaches originally in the web user interface to do that. One was we would just buffer messages. If messages were arriving out of order, we would just buffer the later ones, wait for that message that was out of order to arrive, and eventually flush all of them out, no matter either after a timeout or when that message finally arrived. So we could make sure that the build log would always be showing something and not being delayed because a single message was missing. Because sometimes a single message can actually just be one character. When a build is running and it just outputs a dot, it can just be that character that is actively running. It made our user interface a little bit more complex, but it made the rest of the application a lot simpler. And the logs processing is actually the one process where we broke out all the dependencies and made it a separated process. And I think it has like 30 lines of code in total, which is a lot better than having it rely on a big ball of mud that shares the same dependencies. So in 2013, we're now doing 45,000 builds and per day, which is a pretty good cut, but we're still paying a lot of debt for the initial decisions that we made, the architectural ones. But this brings me back to uncertainty. These architectural decisions, they may look bad in hindsight, but when Travis Yao was built, who knew that eventually it would go from just a few hundred builds per day to almost like 45,000 builds per day. No one knew that. It was an uncertain chapter. No one realized that it would eventually turn into a commercial platform as well. But we still somewhat pay the price. We still have to handle that. We're a small team, but it's just how it goes. It's like I talk about these barriers. I talk about barriers and treating external APIs like your enemies, or treating them like something that could break any time. But that's really hard to foresee when you have no control over the other parts of the system, and it's really hard to make the trade-off between, do I put all of my time in handling all these failures and this uncertainty up front, or do I do that as the system evolves, as I see it break in production? Because I gotta be honest, it's as sad as it makes me to see things break in production. I always get excited about it because I can usually I can learn from it. Now we have better means to actually learn from these incidents and see where our system still needs to be improved. And one of the things where we actually need to improve, and this is one of the last puzzles that we still have, is all of these components still use the same database. Which if you have a diagram where everything points to a single component, that's not good, because when that component breaks, everything will break. And we just had that last week. Our main database fell over because of an EC2 issue, and nothing ran. And this is one of the things we're working on, because our logs processing is now doing up to 300 messages per second at peak times, and that actively affects the reads from our API. So we have this problem where we can easily do 300 writes per second, but being able doing that in our current architecture affects people using our API, people basically looking at our user interface. And that's not a great user experience. But it's another one of these learning experiences. At some point we will hopefully have multiple databases in this setup. And it will all be a little bit easier to isolate these components from each other, because if you look at logs processing, it's a very isolated process. It doesn't do anything. It doesn't do anything that's related to the rest of the system. Logs processing is basically just put all these log chunks into the database, later aggregate them into a big log, and then eventually archive them to S3. That's all that log's doing. It doesn't need to write through the main database. So we have fairly easy means to make our system even more distributed, but by making it so, we'll have to deal with even more uncertainty about which things will break. And we'll have to add more monitoring, and we'll see more failures. But in the end, we will have more simplicity, and these components by itself will be easier to manage on their own than as one big ball of mud. Thank you.
We have questions that came in, so thanks for submitting questions. If you have more questions, you can either ask them live or submit them through your app. Also, remember to vote on your app, vote for the talk. The right answer is green, by the way. Don't tell anybody I told you. So first question, what is the best book or resource for engineers and developers getting into distributed systems? Pitfalls, patterns, best practices?
Let me know when you find it.
It's a really hard question.
Yeah, it is a hard question. I honestly, I have yet to find one. There's not really a good book introducing this kind of stuff. I found a lot of inspiration for how, well, not even just how they have a single algorithm to, you know, handle increment encounters, but I got a lot of inspiration from web operations books, to be quite honest. But I actually started reading papers, like Leslie Lamport's paper. There are some fairly nice reading lists on papers for system engineers out there. I think if you Google them, you will actually find a few blog posts. And these are actually the best resources. Some papers are not very approachable, but Leslie Lamport, for example, he wrote a lot of stuff. That guy, I don't know, he wrote like 100 papers, and
if you go to, you can find his website under Microsoft Research, and he's got all his papers listed. It's an enormous web page.
Yeah. Unfortunately, there are papers like Paxos, you know, where you have distributed coordination, which are not well, at least for me, they were not easy to understand. But I don't know. For me, these papers were the best source of inspiration so far. And one of the actual things about distributed systems in particular, how to handle, you know, when you have parallel processes that talk to each other over the network is, and there's going to be a talk about this, is commutative replicated data types. It's basically data types that can be coordinated, you know, like increment encounter that can be coordinated by multiple nodes, so that you always have an atomic increment in the end. And there's a talk about that tomorrow, I think. And that stuff is fairly interesting for distributed systems because it gives you a good idea of the problems involved with distributed systems in general.
There's also a page under MIT Distributed Systems Research Group. So if you Google DSRG papers, there's a page with a whole bunch of papers listed there. That's a pretty good resource as well. Next question is, are you using circuit breakers, kind of like Michael Nygaard circuit breakers, in addition to timeouts and exponential backoff?
We're not using circuit breakers yet, but it is something that I've been thinking about quite a lot. I love, Michael Nygaard's book is actually one of the better books that you will find on actually running anything in production. Michael Nygaard's Release It. It is, if there's any book I would recommend, it is that book. It mentions circuit breakers and it mentions bulkheads. And circuit breakers is basically the idea when you have too many failures hitting the GitHub API. You trip the circuit and you stop making requests. And after a while you will basically you will start making slow requests again to the API, seeing, you know, gauging out if it's working again, and then at some point you can reconnect the circuit that all of the requests will come through. I've thought about that a lot. We don't have that yet. It's one of these things where what really would be nice, because we have two APIs that we hit like hundreds of thousands of times per day, and the unfortunate thing is that when one of them goes down, we will just keep hitting them. We'll just keep hitting them a lot, and the circuit breaker would definitely be handy. It is something I want to implement for that particular code to isolate these failures a little bit more definitely.
Well, there's a third question, but before I ask it, I have to give a little intro to it, because one of the problems in distributed systems is network partitions. Now, partition can be the failure of a network. It's more generally the lack of an arrival of a message, so a message just might not get to where it's going. Or there's also the fact that a message could be duplicated, depending on what protocols you're using. So this question was asked 3 times. How do you handle multiple processes which need to share the same temporal clock?
Thankfully, we don't have that problem. It makes it fairly easy. I was very happy about that. It's when I mentioned these clocks that we have, it's always only one process that increments the clock. That's we shaved off that problem. So we don't need to have a distributed clock that needs to be incremented, which makes it a lot easier to implement that.
Goes to your simplicity.
Yes.
That's all. Well, let me refresh. Oh, wow, more questions. Okay, wouldn't it be obvious to use a NoSQL database instead? And I didn't ask that question.
To be quite honest, even though I wrote a little book on React, I'm fairly fond of Postgres. It's an awesome database. I'm always surprised that it's actually, we can throw 300 writes per second at it, and it's a 32-bit 1.7 gigabyte EC2 instance, and it can still handle that. But to answer the question, yes, it would be obvious. It would actually be obvious to take our logs process and store the be able to store the chunks in, for example, React instead of Postgres. But the beauty of isolating the logs processing and isolating the separate services is that it doesn't really matter what we use. We can swap it out without affecting the rest of the system. That's the important part about modularity. I can change the data store for one system and it doesn't really affect the rest of the system. That's where I would like to go, and eventually. Maybe we're going to use a NoSQL data store, but in the end, it's just another distributed system we have to take care of, and it's going to bring more problems. So it's always a trade-off.
What kind of monitoring are you doing, and how do you correlate events across the many components?
Oh, it's a painful question.
It's a whole talk in itself.
Yeah, it is a whole talk in itself. So we track a lot of metrics in our system as events happen. Well, we're using that similar to statsd, which is basically a process where all of your processes can send metrics, and it's going to forward them to a system like Graphite, or something that we use is called Librato Metrics, which is a hosted service for metrics. We basically aggregate all these metrics in our applications, and we also have built a custom collector that pulls things like RabbitMQ or a database for information like when was the last build running, how many messages like how old is the queue, how many messages are currently backing up in the queue, because usually when our queue backs up, there's a problem somewhere. And how we track the events through the system is actually a problem that that I'm currently working on fixing. Is we're not doing a really good job at that right now. The problem is that, well, what we're fixing on, what we're working towards is that each request basically gets assigned something as simple as a UUID. It gets assigned a UUID, and then you can use that UUID to trace in the logs what is happening in the system. We don't have a very elaborate tool that allows us to visualize all that stuff. It's more about just being able to retrace these things, because we don't spend a lot of time looking at our logs. We just need to investigate when a customer says, "Hey, I pushed something to GitHub and no build was running on Travis CI," and we need to be able to trace that step back to did a web notification actually arrive, and then what happened to it? And that is one of our biggest problems. And the solution is, again, as simple as assigning a UUID to the request and then using that UUID to trace everything through the system.
How do you test your own system for these kinds of problems, assuming distributed problems?
Another painful question. We don't. We run it in production. That is how we test it.
Well, you might have already. There's a question about thoughts on replacing the central database. You kind of covered that.
Yeah.
What is Gatekeeper doing?
Gatekeeper is it's inspired from Ghostbusters, but Gatekeeper is basically when a request comes, when we get a notification from GitHub that a new commit was made, we basically push that onto a queue, and Gatekeeper takes these commits and turns them into something that is runnable by the system. It basically takes a JSON payload that contains information about a new commit or about a serious commit, and turns it into a set of build jobs that can then be run on any of our job schedulers. And it also does things like synchronizing user data with GitHub. But the main purpose is to be the main entrance point for handling build requests. And
one last question. Are you using AWS as your exclusive platform?
We're not. Our entire app stack runs on AWS. It runs on Heroku. which is always somewhat surprising to people, but we're actually quite easy. We're quite happy with it. Our application stack runs on EC2, but the stuff that is running the tests, which is now 550 test servers, build servers, that runs on a different virtualization architecture. It actually runs in dedicated hardware. But it's still using, we still have an API to talk to that infrastructure, which is kind of handy. It's better than having to do all of the provisioning manually.
That was all the questions that came in. Anybody else have anything? Back there.
So I suppose that RabbitMQ is also a fairly vulnerable component of yours. What do you do to overcome that?
So the question is, RabbitMQ is maybe a fairly, a breakable component in our system. What we do to fix that? Yes, RabbitMQ is a component that used to break a lot, but the problem with that is, our initial problem, I bitch a lot about RabbitMQ, but I think it's more about my dislike of AMQP. It is a very complex protocol. RabbitMQ itself actually worked fairly well for us, but the caveat was that as we run our stuff on Heroku, we use a lot of other add-on services, basically that other people host for us, which is sometimes handy, sometimes painful. With RabbitMQ, it initially was very painful because what these providers usually do is they set up a cluster, which a lot of customers then use. And we rely on getting consistent throughput through RabbitMQ. If we just see a dip in throughput performance in RabbitMQ, our messages will start queuing up immediately, because we rely on that. And in a multi-tenant system, RabbitMQ unfortunately is built in a way that if you have one producer that is producing a lot of messages, it can block other producers or even consumers in the system. So whenever some other customer on that cluster came up and started sending like thousands of messages per second, that immediately would affect us. As soon as we moved to a dedicated cluster that we just had to ourselves, RabbitMQ has not been a problem anymore. And the high availability features in RabbitMQ 3.0 are actually quite nice. I still have my doubts about running it in production. It has its thwarts basically that make it a little bit hard to handle. But when it's running, it actually runs fairly well. They did a lot to make it easier to operate a RabbitMQ in production. But in the end, to us, it doesn't really matter anymore whether we use RabbitMQ or if we use something else, because we're not really tied to it anymore. Removing the requirement of ordering, implicit ordering as the messages are sent through the message bus, allowed us to think about actually using other message buses in the future at some point. But so far, I don't think RabbitMQ will. It will probably easily allow us to do 1,000 messages per second, and we don't have to worry about that. Which I like to not worry about these things for a while, so it makes it a little bit easier.
Okay, with that, it's lunchtime, so everybody thank our speaker.